Hello juniors, today we're going to see a continuation of last class. Remember last class we were talking about transformation of functions in general. We've seen three main types of transformations, which are translations, reflections, and stretches. You remember? Okay, so for this class we're going to see transforming quadratic functions. So we're going to concentrate on one specific type of function, which is the quadratic function, which you've heard about a lot already. So the objectives for today's class: first of all, understand the terms of a quadratic function, and number two, understand the different types of transformation of graphs. Okay, so first of all, let's start defining what a quadratic function is. It says a quadratic function is functions that can be expressed in the form f of x equals ax squared plus bx plus c. This is known as the general form of a quadratic function, which we're going to be covering more in depth during the following classes. Okay, so if we can express a function in this way, then we're talking about a quadratic function. Okay, these are the basic and most important things that you should always have in mind when we talk about a quadratic function. It says the shape of a quadratic function is a parabola, right? The figure we see over here, this is called a parabola, which, as you know, may be either like this or downwards like this. Okay, both are examples of parabolas. So let's identify the most important thing you should always consider when talking about quadratic functions or parabolas. First of all, the general form of a quadratic equation, the one that's written there, right? If we analyze each of these terms, A is the most important one, because it tells us the shape or the shape or where the quadratic function will open up, right? If a is a positive number, which means that a is greater than 0, then the function faces upward. And an easy way to remember this is that if a is positive, then we have a happy face, right? The parabola opens upward. But if a is negative or a is less than 0, f of x faces downward. Okay, if a is negative, we're talking about a sad face, right? The parabola opens downward. Okay, then we have this term, the letter c, which is also very important, in which, like in a linear function, when we talk about the independent term, the term that does not have an x, the independent term always represents the y-intercept. Okay, so same thing as a linear function, the letter c in a quadratic function represents the y-intercept. That's when the parabola crosses the y-axis, right? Okay, so maybe I should write that here. Y-intercept is 0, c. Okay, so the parabola has something called the vertex, which, if we read the definition, it says vertex is a turning point of the function, either a maximum or a minimum. So it's this point over here, which represents the maximum or minimum of this function. In this particular example, this represents a minimum, right? It's the lowest point of the function. Then we have something called the axis of symmetry, which it says is a vertical line that passes through the vertex. We would always have this for a parabola. It's like a mirror that divides the parabola into two equal parts, right? This part over here and the reflected part, this part over here. That's the axis of symmetry, and it always passes through the vertex. It's a vertical line that passes through the vertex, okay? Then we have two very important points in this case, which are called the roots or x-intercepts of the function, of the quadratic function, okay? And it's basically where the parabola crosses the x-axis, if it crosses the x-axis, because there are some cases in which the parabola does not cross the x-axis, and in those cases there are no roots, okay? So there are different ways to call this points here. We could call it root, we could call it solutions, we can call it the x-intercepts. Those are the names that are usually used for these 2 points. And what is the characteristic of these 2 points? That f of x or y, f of x equals 0, right? Y is 0 in those points, okay? So that's how we calculate the roots of a quadratic function. We're going to see this in the following classes as well. Finally, we have another important point, which is this one, the y-intercept, okay? It's where the parabola crosses the y-axis. And in a quadratic function, the y-intercept is always the point 0c, where c corresponds to this term over here, the independent term of the general form of a quadratic function. Okay, so those are the basic things you need to know about a parabola or a quadratic function. These are some real-life applications I thought of for quadratic functions. For example, a very common use of quadratic function is projectile motion, right? When we throw objects or when we kick a ball or when we launch a rocket, for example. Those are all examples of projectile motion. And also a car's value. If you see, this is half of a parabola, right? This is also a quadratic function if you want to see it that way, okay? So these are real-life application of quadratic functions. If you may think of other examples if you want, but these are the ones that I thought about for this class. Okay, here it says the data gives the predicted height h of a model rocket t seconds after it is launched. Okay, so this is another real-life application of a quadratic model. Variables h and t are connected by a quadratic function, and the graph of h against t is a curve shape called a parabola. Okay, so if we make a table, an experiment where we launch a rocket into the air, if we calculate the time it takes in the air and the respective height at each time interval, then if we plot this point, we're gonna get this parabola, which models the motion of the rocket throughout time, okay? Then it says this parabola is concave down and has a maximum point. So in this case, this is a maximum point over here. This is the vertex of the parabola. This is the axis of symmetry, okay? So the parabola is concave down and it has a maximum. A parabola may also be concave up and have a minimum point, which was this example over here, right? Okay, then we're getting into the important part of this class. It says the simplest quadratic function or parent quadratic is the function f of x equals x squared. Remember, this is something I always tell you. The parent function of any function is the simplest form of that function. And in the case of a quadratic function, it is f of x equals x squared, which is the same as saying y equals x squared. This function is the one that you can see in this graph over here. And it says the graph y equals x squared is shown. The vertex is 0, 0. When we're talking about a parent quadratic, the vertex is always the point 0, 0. And it is a minimum point. Why is it a minimum? Because if you take a look at this function, y equals x squared, you would see that the a, which is in front of the x, is a 1, right? And this 1 is a positive number, meaning that this should be a happy face, right? That's why the parent quadratic has this shape and not this shape, right? Okay, so the vertex is 0, 0, and it is a minimum point, and the axis of symmetry is, if you see, is the y-axis for the parent quadratic. The equation of the axis of symmetry is x equals 0. Remember, when we want to write the equation of a vertical line, it's always x equals something, x equals b, for example. But in this case, since we're crossing through the y-axis, this corresponds to x equals 0. Okay? So that's the parent quadratic. Now let's see transformations applied to the parent quadratic. Remember the different types of transformation we talked about during the last class. Translations, reflections, and stretches. 3 types of transformations. We're going to see now how they apply to quadratic functions. So, translations first of all. It says the graph y equals gx is a horizontal translation of the graph y equals x squared shifted 3 units to the right. So you see here we have the parent function y equals x squared, and the green function, you see that it is translated 3 units to the right, right? An easy way to see this is by comparing the vertex of both parabolas. The first one is at 0, 0, and the new one, we move 3 units, 1, 2, 3 units to the right. Okay, so how do we rewrite this equation? It's just x minus 3 squared, right? Remember that for a horizontal shift, we need to apply this form, f of x minus 3, okay? And that will shift the function 3 units to the right, okay? Oh. Next example. It says the graph of y equals gx is a vertical translation of the graph y equals x squared shifted 2 units down. So now in this case, we see that the original function, the parent function, y equals x squared, is shifted 2 units down. If we compare the vertex of this original function with the vertex of the new function, we see that we go down 2 units, okay? So the equation of gx would be rewritten this way, x squared minus 2, okay? The minus 2 is outside the parentheses if we want to make a vertical shift, okay? So remember those rules for transformations. We're going to be applying them a lot for all the different functions we're going to be covering in the IB program. Okay, then we have reflections. It says the graph y equals gx is a reflection in the x-axis of the graph y equals x squared, which is the parent function. So how do we obtain a reflection of any function? We just need to write a negative sign in front, okay, minus f of x, right? So gx, the new function, would be, instead of x squared, it's minus x squared, where the minus should be outside of the parentheses that affects the square power, okay? So this graph, the green one, is g of x equals minus x squared. It's a reflection on the x-axis. The x-axis acts like a mirror in this case. And then finally we have stretches. It says the graph of y equals gx is a vertical stretch of the graph of y equals x squared with a scale factor of 2. Remember that when we have a scale factor of 2, that's a vertical compression, right? You see that the green function is now closer to the y-axis than the original function, which is the purple one, okay? Each point of the graph of g is twice the distance from the x-axis as the points on the graph y equals x squared. When the scale factor is less than 1, the graph of g of x is a vertical compression, okay? So this is what we see here. You see that, for example, point 1, 1, 1 in the original graph, for the new function would be at 1, 2, right? The value doubles itself, and doubles in y, okay? So for example, this point over here, 2, 4, for the new function, it'll be 2, 8, right? 4 times 2 is 8. So each of the y coordinates are doubled in this case, okay? So that's stretches. Now let's analyze some conceptual questions for you to try to start internalizing this concept. Question number 1 says, factual. What effect do A, H, and K have in transforming the graph y equals x squared to the graph y equals A times x minus h squared plus k? So pay attention at this equation written here. what is the function, or yes, the function that this letter is doing here? What kind of transformation is A doing to the graph? If you see, if A, for example, has a negative sign in front, we're gonna be applying a reflection, right? We're multiplying but by a negative number in front, so we're doing a reflection. And if A is a number different from 1, we're going to be applying a stretch, right? A stretch. In this case, for example, we had the value of A was positive 2, so the graph was stretched, right? So that's the function of letter A. Then this h over here, which is inside the x of the function, what it does is it makes a horizontal shift, right? H units to the left or to the right, depending on the sign of the number. And finally, k, as it is outside of the function and we're adding a value k, what the k is doing is a vertical shift, right? K units up or k units down, depending on the sign of k, sorry. So let's read the answer for this part for you to understand this better. It says, the student's answer may be in their own words. Okay. When a is less than 0, meaning that a is negative, there's a reflection in the x-axis. Okay. When a, the absolute value of a, is greater than 1, there's a vertical stretch with a scale factor, absolute value of a. When the absolute value of a is a value less than 1, there's a vertical compression with scale factor, absolute value of a. When h is positive, there's a horizontal translation to the right, okay? And when h is negative, there is a horizontal translation to the left, okay? Finally, when k is positive, greater than 0, there is a vertical translation up k units. And when k is less than 0 or k is negative, there is a vertical translation down k units, okay? So try to remember this equation over here, and if you understand this well and what each of the letters represent, this will be very easy for you to solve. Okay, let's see the conceptual question number 2. Without using your GDC, sketch the graph y equals x squared. Then apply the transformations in the order given. Okay, so we're not going to sketch the graph, but what I want to do is write the equations for part A and part B, given all of these conditions of transformations. So without sketching, let's try doing this. We're going to write an equation by applying these transformations first. For part A, it says a vertical stretch with scale factor 2, horizontal translation right 3, vertical translation down 4. Write down the equation of the final graph. Okay, so for part A, if I write this equation, which we're gonna be always using for quadratic models, I'm going to write this as, yes, I'm going to write y equals a times x minus h squared plus k. So in part A, what do you think should be the value of a according to the sentence we have there? The value of a should be 2, right? Because we have a vertical stretch with scale factor 2. Okay, so this would be y equals 2 times x. Then it says horizontal translation right 3 units, okay? So the value of h would be this 3 over here. So minus of the formula, 3. Remember that when we have minus something, we're moving to the right, okay? So this is correct. And then it says vertical translation down 4 units. As it says down 4 units, the value of k should be negative 4, okay? We're moving down, so minus 4. This would be the equation of this graph, okay? If you do this graph, maybe you can try this on your own using the calculator, you would get a graph that is translated 3 units to the right, vertical shifted 4 units down, and it will be stretched vertically by a scale factor of 2. Okay. Part B. It says horizontal translation right, vertical translation down 4, and stretch with scale factor 2. Write the equation of the final graph. Okay, so it's the same thing, but the thing is that it is changing the order in which we're applying the transformation, and that's something very important that you should always consider. But as we're not graphing this, I will not be able to show you this, but I'm gonna explain it in question number 3. So we're gonna leave this apart. The equation would be the same thing. It's just 2 times x minus 3 squared plus minus 4. Okay, so we're just gonna leave it like this for now. Then it says for question number 3, conceptual. Does the order in which the transformation of the graph of y equals x squared to the graph f of x equals a times x minus h squared plus k are completed matter? Explain why or why not this is the case. Okay, so this is exactly what we had here. You see that we had the same types of transformations, but the order in which they were given varied. And the question is if the order in which I apply this transformation matters or not. And the answer is yes. We're going to read the whole answer here. It says, yes, it matters. The graph in question 6 shows that you do not get the same result when you perform the transformations in a different order. Students may not be able to articulate the reason until they have had practice with some of the exercises. The result in the first graph in question 6 is a graph y equals x2 times x minus 3 squared minus 4. In the second graph, when the vertical stretch is applied last, the graph of y is 2 times x minus 3 squared minus 4, which is the same as this. If we do the distributive property, we're going to get this graph over here, this function over here, which is something different from this, which we got in part A. So the graph would be different. When graphing y equals a x minus h squared plus k using order of operations, you would perform the horizontal shift h, the vertical stretch a, and vertical shift d. You will get the same graph if you perform vertical dilations first and then follow the translations. Reflection in the x-axis and vertical dilations must be performed before vertical translation. Okay, so this is the most important part that you should always have in mind. Whenever you're applying multiple transformation to a function, always do the vertical translation last, okay? Last. If you perform this at the beginning, you will get a wrong graph, okay? So always, I would always recommend you to do the horizontal translation first, then you would do the vertical stretch, if there's any, and last, you're gonna apply the vertical translation, or else you're gonna get a wrong graph. Okay, then it says, the graph of any quadratic function can be obtained by applying the combination of the following transformations to the graph of the parent quadratic y equals x squared. Okay, so this is just a brief summary of what we were studying. Transformation of y equals x squared. If we want to reflect this graph on the x-axis, it's just adding a negative sign in front of the parent function. If we want a vertical translation, we add a value k. If the value of k is positive, it moves up. If the value of k is negative, it moves down. Then vertical stretch with a scale factor absolute value of a. If we multiply this number, any number to the parent function, we're going to get a vertical stretch if the absolute value of a is positive, is greater than 1, and a vertical compression if the absolute value of a is between 0 and 1. Finally, we can apply a horizontal translation by adding or subtracting a value h inside the x value, okay? And the function is going to move right if h is positive, and it's going to move left if h is negative. Okay, so this is the most important thing you should remember. The general formula to apply quadratic transformation is this one over here, which we have seen already, where A determines the concavity of the graph. If A is positive, it will be concave up. If A is negative, it will be concave down. Okay, happy face, sad face. And also, the value of A determines, I forgot to write that, the value of A, I'm going to put in absolute value, determines the vertical stretch of the graph. Okay. Then the value of h is the x-coordinate of the vertex of the parabola. We're going to see this in a second. And the value of k is the y-coordinate of the vertex. So remember this, the vertex of a transformed parabola has coordinates h and k, where h is the horizontal translation of the graph and k is the vertical translation of the graph. Okay, so let's see this example. This is example 16 of the book. It says, sketch the parent quadratic y equals x squared and the graph of y equals gx on the same axis. Then write down the coordinates of the vertex and the equation of the axis of symmetry for the graph of g. Okay, so just not to waste too much time, we're not going to graph the functions. I'm just going to show you the results for the graphs. But what I want to do here is to start analyzing the functions in order to try to at least imagine how the graphs would be before even graphing, okay? So if you see, for example, part A, gx equals half of x squared. What do you think, what type of transformation is this 1/2 doing to the parent function x squared? If you paid attention to the explanation, this corresponds to a vertical stretch, right? And there is no horizontal nor vertical translation of the graph. So the parabola should be, imagine this is the original function, the parent function. This new function, which I'm gonna graph using green, should have the same vertex because there was no translation of the graph, but there should be a vertical stretch. So the graph would look something like this. It'll be same vertex, but it'll be a little bit more wide, right? So meaning that the values will be further apart from the y-axis, okay? So you can see this here, you see? It says the vertex is the minimum point of the graph of G. The axis of symmetry is a vertical line passing through the vertex. A is 1/2. That means that that's a vertical compression with scale factor of 1/2. So we forgot to do that. Write down the coordinates of the vertex and the equation of the axis of symmetry, okay? So the vertex is the same as the parent function, which is always 0, 0, right? So the coordinates of the vertex in this case would be 0, 0. So the axis of symmetry is always the x coordinate of the vertex. So we would say that the axis of symmetry in this case is x equals 0. I'm going to move this up here. So the axis of symmetry is x equals 0, which is what we get here. Axis of symmetry, x equals 0, vertex 0, 0. Okay. Then, here it says each point on the graph of G is half the distance to the x-axis as the corresponding point on the graph y equals x squared. Okay. Part B. We have this equation, g of x equals x plus 3 squared minus 2. So what types of transformations with respect to the parent function do you think are happening here in part B? If you pay attention, you would see that there is no value of a, right? So there is no vertical stretch nor compress. But we have these two terms which correspond to h and k. That means that they are both horizontal and vertical translations. So if we analyze where the function moves, let's say that this is the original, the parent function, okay? If this is a plus 3, it means that the new parabola is shifted 3 units to the left, right? So we're going to move 3 units, 1, 2, let's say 1, 2, 3, somewhere around here. And then this negative 2 says that the parabola moves 2 units down, right? So 1, 2. So our new vertex would be here, right? So the shape of the parabola is the same because we only had a translation. So the parabola would look something like this. It'll have the same shape, but the vertex would be translated 3 units to the left and 2 units down. So we're going to get that parabola over there. So our new vertex will have coordinates negative 3, 3 to the left, comma, negative 2, 2 down. And the axis of symmetry would be always the x coordinate, x equals negative 3. Okay? So let's see the resolution here. You see that we get the same idea, same graph. It says gx equals x plus 3 squared minus 2, h equals negative 3, horizontal translation to the left 3 units, k equals negative 2, that's a vertical translation down 2 units. So the axis of symmetry is x equals negative 3, and the vertex is negative 3 comma negative 2, which is the same thing we got here. Okay? This is how I quickly analyze the problem without having to use a calculator to sketch the graphs. Okay? So let's see part C. Part C says gx equals 2x squared plus 3. What can we see here? First of all, there is a value of a, which is 2. That means that there is a vertical stretch. And as 2 is positive, the parabola will still have the same direction, meaning that it will be a happy face as the parent function, right? And then this plus 3, as it is not affecting the x, this plus 3, what it does is it shifts the parabola or the vertex 3 units up, right? So it's a vertical translation. So if I make a quick sketch of this situation, I would say that the original function would be something like this, the parent function, and the new function should be shifted 3 units up. And as this is a 2, which is a number greater than 1, we're going to get a vertical compression, meaning that the parabola would be narrower than the original. So this would be, let's say this is our vertex and I move 3 units up, 1, 2, 3, so my new vertex is here, and the parabola should look narrower, so it would be something like this. Okay, that is the idea. So our new vertex will have coordinates. It doesn't move in x, it just moves in y, so this would be 0, 3. So the axis of symmetry, always the x coordinate is x equals 0. Remember to always write x equal the value for the axis of symmetry because it's a vertical line. Okay, so this is how the answer should look like. Let's see. Yes, this is exactly what we get. So it says g of x equals 2x squared plus 3. The absolute value of a is 2, meaning that it's a vertical stretch with scale factor 2. Each point on the graph of y equals 2x is 2 times the distance from the x-axis as a corresponding point on the graph of y equals x squared. K equals 3 represents a horizontal translation up 3 units, which is what I told you. So the axis of symmetry is x equals 0 and the vertex is 0, 3, which is exactly what we wrote here. Okay, finally, for part D. it says gx equals negative 3x squared. Okay, so the first thing I see is that there is no value of h and there is no value of k, right? So there's no vertical nor horizontal translation. That means that the vertex remains at the same coordinates, right? It will be 0, 0 again. Then, if we analyze this negative 3, the negative sign is telling us that the parabola changes direction. So in this case, the new parabola would be facing down. It will be a sad face. And the 3 corresponds to a vertical stretch, meaning that, as this one over here, the new parabola should look narrower than the original. Okay, so if we graph the parent function looks something like this, and the new function should look something like this. It should be narrower. Let's make it narrower and facing down, because there's a reflection on the x-axis, right? So this is what we should have as a result. So the vertex remains the same. It is 0, 0. And the axial symmetry is also x equals 0, right? So it remains the same as the original. So let's see the result. You see we get exactly that, right? It's reflected and it's narrower than the original. It says g of x equals negative 3x squared, which is the same as saying minus 1 times 3x squared. A equals negative 3, that's a reflection in the x-axis, and the absolute value of a equals 3, which represents a vertical stretch with scale factor 3. Each point on the graph y equals gx is 3 times the distance from the x-axis as a corresponding point on the graph y equals x squared. So the axis of symmetry of the function, of the new function, is x equals 0, and the vertex is 0, 0, which is exactly what we had here. Okay? So this is a quick guide for you to understand how transformations work. And okay, so I hope you understood this. Okay, we still need to do one last example. Yes. Okay, there's a hint here for you to always remember, and it's what I already told you. It says, when a question asks for the equation of the axis of symmetry, the equation will be given in the form x equals something. Students often lose marks on exams for writing things like axial symmetry equals 2, or just writing a number rather than an equation. Remember that when you're writing the equation of the axial symmetry, you should always write x equals something. Okay, let's say 2. Okay, do not write just 2 for the equation of the axial symmetry, because remember, it's the equation of a vertical line, and the equation of a vertical line is always x equals something. Okay, so don't forget that. You should always write x equals and the value of the axis of symmetry. Okay, then we have this second hint, which is something I already told you last class. It says translations can be represented by vectors in the form hk, for example 0, 2. What does that represent? It represents a vertical translation 2 units up, and okay, and yes, 0 units horizontally. Or for example, the vector negative 5, negative 3 represents a horizontal translation of 5 units to the left and a vertical translation of 3 units down. Okay, that's how we interpret translations given as vectors in this case. These are vectors. Finally, example 17. It says, let f of x be x squared. Describe a series of transformations which map the graph of y equals f of x onto the graph y equals gx. Then write an expression for the function gx. Okay, so we have the parent function as always, and we want to know how to get this green function over here by applying the different types of transformations we know. Okay, so I'm going to show you how I would think about this, and then I'm going to show you a short video which also explains the same problem. Okay, so I have the parent function, right? The first thing I would do is compare the vertex of both, okay? The original parent function would always have vertex 0, 0. And you see that the new function has vertex here, which has coordinates -4, 0. That means that there was a shift, a horizontal shift 4 units to the left, right? Because the new vertex has that new position, okay? So if you think about, always think about this equation. Gx, in this case, equals a times x minus h plus k. Always think about this equation. So we already know that there's a horizontal shift 4 units to the left, so the value of h should be -4, right? We also know that there is no vertical translation because the y coordinate of both vertices are the same, right? So k in this case is 0. And the other thing I notice is that this parent function has the same shape as this function over here, but they are going in opposite directions, right? This is a happy face, this is a sad face. So that means that there's a reflection on the x-axis, and the value of a therefore is -1. Why -1? Because both parabolas have the same shape. You see that none of them is narrower or wider than each other. They have the same shape, right? But they are looking in opposite directions. So the value of a in this case is -1 because there's a reflection on the x-axis. Reflection on x-axis. So finally, the function of g of x would be minus x plus 4. Oh, I forgot here, squared. Okay, this is the function that maps this graph into this graph over here. Okay, I hope you could understand that. Then we're gonna see example B. I think, yes, we're done after this. This is example B. So we want to do the same thing. We want to translate the original function into this new green function over here. Okay, so first analysis I always do, look the vertex. The parent function always has vertex 0, 0, and our new function has vertex 3, 2. That means that there was a horizontal translation 3 units to the right and a vertical translation 2 units up. Okay, so if we think about our function as always, gx equals a times x minus h squared plus k, we already know that h should be 3 and k should be 2. Okay, now we need to see the value of a. First of all, I see that both functions are facing upward. They are both happy faces, so the sign of a would be a positive number. Okay. Second, I would see the shape of both parabolas. In this case, we see that this green one is a little bit wider than this one. So there should be a value of a different from 1. There should be a scale factor in this case because they do not have exactly the same shape. So what do I see? For example, if I observe the green parabola, I would see that if I start from the vertex and I go 2 units to the right, or to the left or to the right, doesn't matter, we see that this function goes up 2 units, right? But if we do the same thing for the red parabola, we would see that if we go to the right 2 units, to the right or to the left, it doesn't matter, let's go to the same direction, to the left, 1, 2. What happens here? I go up 1, 2, 3, 4 units. So we go twice as much as we would go in the green parabola. Okay, that tells me that the value of a should be 1/2. because remember that the scale factor of 1/2 means that this green parabola moves half as much as this green as the original red parabola, right? If this moved 4 units up, this moved 2 units up, so that's half. So the value of a would be 1/2. Okay, so finally the new function, the green one, would be 1/2, positive 1/2, because they're both happy faces, times x minus 3 squared plus 2. This would be the new equation that maps the parent function, the red one, into the green one, okay? The translated function. Okay, so I hope you could understand this. If you didn't understand this explanation, I will show you a short video about a professor that solves this same problem. If you understood this, you could just pause the video here, and that will be it for today's class.
Part A. To describe the series of transformations which map the graph of y equals f of x onto the graph of y equals g of x, where f of x equals x squared, first consider the vertices of both graphs. You can see that when the vertex of the graph of f, 0, 0, is translated 4 units left, it coincides with the vertex of the graph of g, negative 4, 0. In addition to translating left 4, there is a reflection in the x-axis. Notice that the graph of g has the same size as the graph of f, and therefore there is no stretch or compression. To write an expression for the function g of x, consider the constants in function. G of x equals a multiplied by x minus h squared plus k. The translation 4 units left implies h equals negative 4. No stretching or compressing, and a reflection in the x-axis implies a equals negative 1. There is no vertical translation of the graph, and so k equals 0. Substituting these values gives g of x equals negative 1 multiplied by x minus negative 4 squared plus 0, which simplifies to g of x equals negative x plus 4 squared. Part B. Notice that when the vertex of the graph of f, 0, 0, is translated right 3 units and up 2 units, it coincides with the vertex of the graph of g, 3, 2. There is no reflection of the graph of f in the x-axis, but there is a vertical compression with scale factor 1/2. Considering a correct order of transformations, the graph of y equals g of x can be obtained from the graph of y equals f of x by translating right 3 units, a vertical compression with scale factor 1/2, and translating up 2 units. To write an expression for the function g of x, you know that a translation right 3 units implies h equals 3. A vertical compression with scale factor 1/2 implies a equals 1/2, and a translation up 2 units implies h equals 2. Substituting these constants into the function g of x equals a multiplied by x minus h squared plus k, you get g of x equals 1/2 multiplied by x minus 3 squared plus 2.